Okay, now let me switch back to the main flowsheet tab. In this video, the first update we will make to our simulation is the addition of a third mixer so that our process will look like this. We will add the third mixer such that it combines the two streams of acetone and MIBK mixture from the two flash separators, flash 1 and flash 2. Okay, now to add an additional mixer, go to the model palette and click on the mixer icon. Then bring your mouse inside the main flowsheet and click here where you want to add the mixer. Now right-click again to cancel the insertion mode. Here I'm going to rename this mixer as Mixer 3. Then I'm going to resize it a little bit like this. And now we need to hook this stream here and this stream here to the mixer. So right-click on the first stream here, then click on Reconnect, and then Reconnect Destination. Now click here on the red arrow to hook the stream to the Mixer 3. Now let me just change the location like this. And now to hook this second stream here, right-click on it, Reconnect, Reconnect Destination, then left-click here. Now let me just a little bit change the arrow here, and let me rearrange this one here like this. Okay, so now we have added our additional mixer, then connected it to the two streams coming out from the flash 1 and flash 2. Now we need to add a second stream or a third stream, which is the mixer exit stream. So click on material icon, then point on the red arrow, click on it, then drag your mouse and click here again. Now right-click again to cancel the insertion mode. Finally, I'm going to rename this stream here as 3mix3. Okay, now the next piece of equipment in our process, and as you can see here from this simplified diagram, is a distillation column. Recall, Aspen Plus provides several options when simulating a distillation column. At this point, save your current Aspen Plus simulation project under 3 names. We will use the first version to complete a distillation with the DSTWU distillation column, the second with the DISTL column, and the third one with the red frag column. So I recommend you that you save them with names that reflect the distillation method being used. Remember to save your work, go to File, then click on Save As, and then I recommend you to choose Compound File. Okay, now in this first version, we will add a distillation column using the DSTWU operation unit. To do that, select Columns from the model palette, then click on the DSTWU icon and place a DSTWU column into the process flowsheet window, as you can see here. Then right-click to cancel the insertion mode and resize your column. Now we will connect the product stream from the third mixer that you can see here to our new added column, and then add in 2 product streams where Aspen Plus indicates that they are required. So to connect this stream here to the column, right-click on it, then Reconnect, Reconnect Destination, and then click here on the red arrow. Now let me rename this column here as DSTWU1, and then I will add 2 streams. So I will click on the material icon, and then as you can see here, I need 2 streams, one here and one here. So I will bring my mouse and hover on over the red arrow, click on it, then click here again, then click on it here, then click here again. Notice here that I will be also adding a third product stream of the condenser that you can see here with the blue arrow to account for any free water that can be separated from within the condenser. So click on the blue arrow, then left click again here. Now I'm going to rename these new streams. So S1 will be renamed DSTWU, and I will put bottom BTM, and then S2 will be renamed DSTWU top, and then this stream here will be renamed DSTWU water H2O. And let me rearrange these streams a little bit. Okay. At this point, your flow sheet should look similar to what you see on the screen. Notice now that we are only required to update our data input in the Blocks tab, because you can see a half-filled red circle next to it. So now click on the Reset button that you can see here to reinitialize the simulator. So select Simulation, then click on OK, and then click again on OK. Now you can click on the Next button, and this will open up a tab to input the properties or the operating condition for our distillation column. For this simulation, we will be inputting the number of stages that you can see here, the key component recoveries that you can see here, and the tower pressures. In our case, the condenser and reboiler operate at pressures of 1 and 1.4 bar respectively. So here, let's put 1 and select bar, and here we'll put 1.4 and select bar. Now, as a first approach, we will start with the number of stages equal to 24, and then vary the number until the required degree of purity is achieved for acetone. So here, type in 24. Next, for this box here, the component recovery values that are input are equal to the amount of each component in the distillate divided by the amount of each component in the feed. For this reason, a recovery of 99.5% for acetone and 1% for the MIBK are applicable if our distillation tower is operating well. So, for the light key, which will be acetone, click here to expand the list, then select acetone, and type in here a recovery of 99.5% or 0.995. Then for the heavy key, it will be MIBK, so expand the list here, then select MIBK, and type in here a recovery of 1% or 0.01. Okay, notice now that the simulation status changed to required input complete, indicating that Aspen Plus has now all required input data and is ready to run the simulator. You can also see here the presence of a blue check mark next to the blocks folder. Now, for our benefit and before starting the simulator, we would also like Aspen Plus to produce a table of reflux ratio versus the total number of calculated theoretical trays. This can be easily done by selecting the Calculation Options tab that you can see here at the top of the DSTWU input window. So click here, then check the box corresponding to this calculation, which you can see here, generate table of reflux ratio versus number of theoretical stages. At this point, our simulation is complete, so click the Reset button, click on OK, then click on the Run button to run the simulation. Now, you may get warnings like the ones that you can see here. The first two are related to the input data we have specified for our distillation column. Don't worry about them right now, we'll fix them in the next run. And the third one that you can see here can be easily removed if you set the free water option to yes. To do that, go to the Setup, then Specification, and then go to the Global tab. And here, Free Water, expand the list, and select the option Yes. Actually, when you select Yes, Aspen Plus will perform calculations to handle free water as a second liquid phase in water organic systems, which is our case here, since we added a third product stream off the condenser to account for any free water product that can be separated from the organic product, which is acetone, within the condenser. Now let's reset our simulator and then rerun it again. As you can see here, we have removed the error related to free water, but we still have errors associated with our input data we specified for our distillation column. Don't worry about them right now, we'll fix them in a moment. Now, even though we have some errors, we will edit the report and check these preliminary results. To do that, click on Stream Summary button, and the results will be displayed in the form of a tab. Okay, so far we will only focus on the stream exiting the distillation column overhead, which we tagged DSTWU top. The result column associated with this stream is highlighted here. Recall, we look for a desired purity of 95% weight acetone. So let me scroll down and look for the mass fraction results. Click here to expand the list and see the mass fraction for each individual component. As you can see here, with the initial input parameters we have specified for our distillation column, we were not able to achieve the desired 95% purity of acetone in this first simulation. Therefore, we have to manipulate the input parameters by trial and error procedure to achieve the required target of acetone mass fraction equal or higher than 95%. Recall, these input parameters include number of stages, tower pressures, and key component recoveries. So what I suggest you now, pause the video, try the trial and error procedure on your simulation until you finally meet the required purity of acetone, then come back to the course and check or compare your results with what I am going to show you next. Okay, after several trial and error attempts, I have found the following new input parameters such that acetone mass fraction in the top stream is 0.96 and MIBK mass fraction is 0.99 in the bottom stream. Basically here, I have increased the number of stages from 24 to 36 for enhanced separation and slightly reduced the condenser and reboiler pressures from 1 to 0.5 bar for the condenser and from 1.4 to 1.2 for the reboiler. Now if I edit the results, you can see here for this stream here, the top stream, and if I go to mass fraction, that now my acetone yields a mass fraction of 0.96, and for the bottom stream, my MIBK yields a mass fraction of 0.99. Now, to have access to more detailed results about the design of our distillation column, go to Blocks, then DSTWU, then Results, and then Summary tab. Here you have access to several information, such as the feed stage number that you can see here, which is in our case 17, and the reflux ratio that you can see here, which is in our case 1.4. Finally, you can have access to the reflux ratio profile for our column by clicking on the reflux ratio profile tab that you can see here. Now, the principle of operation of distillation columns is beyond the scope of this course, but keep in mind that there is a trade-off between the number of stages and the reflux ratio. Each additional tray will add up to the equipment cost, while the increase in reflux will add up to the operating costs of the column. Now, we will use some of this information in our input for the DISTL column that we will cover in the next video. Finally, before to finish off this video, I would like you to keep in mind that because of the simplifications that are used in the model of DSTWU, the design specifications will not be appropriate. Now, despite the fact that this shortcut method appears to provide a quick way to obtain satisfactory results, it does not always guarantee the accuracy that we are looking for. For this reason, any case study in the form of design specifications, sensitivity analysis, or optimization should be carried out using rigorous models such as the red frag column.